Okay, good morning. Today is October 28th, and there was some confusion yesterday about if we had the class or not. That's why I sent you last night an announcement remembering you that since next Monday, there will be holidays. We will miss that class. And because of that, I decided to have today class. So I'm seeing that the number of students is relatively low. So what I'm going to do is let's comment on the text, okay? And then let's go on with the material. Oh no, let's go the other way. No, that's okay. Because so if somebody else comes, then he will listen to the explanation of the new material. Okay. Can you see my PowerPoint screen, people?
Yes, doctor.
Yes, okay, doctor. Thanks. Okay. So, okay, let's see if we can do this. So today is October 28th. Let me write here just to check after the quiz number 1. Okay, so anybody, how do you remember the errors, the problems that we had in the source code that I gave you? Does anybody remember the errors? Anybody? Anybody remember does anybody remember any of the problems in the code? Anybody? Anybody?
Yes, doctor. And I have 2 errors, syntax error.
Okay.
In the bracket in print,
okay.
in the table list.
So there was some missing characters. Okay. The second one was about how can you improve the exactness of the calculations. Anybody? Anybody, please? How can you improve the exactness of the calculation? Anybody, please? Anybody? Mr. Ortega, what did you answer in this question? Mr. Ortega, are you there?
Yeah.
What did you answer for this? You didn't answer this? No? Would you please raise your hand if you answered this question? Okay, there is somebody who had problems. Okay, Mr. Ortega had internet problems. Anybody else? Did anybody answer this question, please? Yes, no? Ms. Vera, did you answer this question?
Good morning, doctor. Yes, I answer, but I think I
I don't make it right.
Okay,
Sorry.
so no problem, no problem. You don't need to say sorry. The thing is this, okay, you were trying to find, oh man, what did I do? Okay. Damn it. Basically, what you're trying to do is this. See, let's suppose that you have x and this is f of x. Okay. So you're trying to find the solution for that. So that's the value that you're trying to find. So let's call it x star. So what you do is you say, if you start with one approximation, okay, what you do is, for example, you start here. Okay, this is your xi. This is your ith approximation. So you divide this by the function evaluated at that point, and you divide it by the derivative of that at that point. And then what you do is you calculate the error is the absolute value of the difference. Okay, so what we have to do is take this difference and try to make it less than the tolerance or the maximum error. Okay, if this is correct, then you stop. If not, you have to go again and try it again. So there was a variable or a parameter, we call it tolerance. And we set this value equal to 10 to the minus 4, I think. Genesis, do you remember this value? It was 10 to the minus 4?
Yes.
Yeah, so what you need to do is, in the code, what you need to do is take this value and put it, set it equal to a lower value. That's what you need to do.
I have a question.
Yeah, go on.
In that case, the exactness for the solution or more, or I don't know, the value of tolerance, what is the correct value for to say that this is a more exact? Because I write a value more lower than that minus 4, but I say that that's depend on you, I think, because that can be
You'll never reach exact this value.
yes,
Why?
for that, yes.
The problem is that this x is a real variable. Okay, so that means that if you need to specify this variable, you need to specify, since it is a real variable, you need to specify an infinite number of decimals, and you never reach that. So what you can do is you can accept that you're going to be here, and that you're going to be very close. See, you're going to be very close to that value. Okay, and this distance is lower than this value. That's all what you can do. The problem is that if you choose a very small value, for example, let's suppose I take this value equal to 10 to the minus 20. Okay, so that means that the computer has to keep in its memory at least 21 values for the decimals, right? And the problem is that, I don't know what about Python, but for example, in Fortran, when you work with common real variables, the number of decimals that for a common real variable, it's 7. So if you try to go with an error lower than, say, 10 to the minus 10, it won't be possible, because the computer does not have enough memory to keep all of this information for a number. Okay, if you want to get more information, what you have to do is you have to declare a double precision. That means that you basically go to, I think it's 16 decimals. But still, if you want more precision, the computer is not going to be able to do it. So basically what you have to do is you have to accept that difference is going to be there. You will never be able to take this such that the error is 0. But you can set it equal to a value, the difference equal to a value smaller than this one. And if this is small enough, this difference eventually becomes neglectable. Okay, that's all what we can do, because these are real variables. I don't know if I answered your concern. Who's this, please?
Dr. Ordóñez.
Okay. Okay, and the last questions about this was how can we put this information in an external file? External file for results. Mr. Mateo, are you there? Mr. Mateo?
Yes, doctor.
Did you answer this question?
No, doctor.
Okay, I don't see your, could you please turn on your cameras if possible? Because I have very short memory, so I know I said hello yesterday, but it's it's difficult for me to remember each one of your faces. So please, would you please turn on your cameras if possible? In some cases, I understand there are some problems because of the connections. But if you can, please turn on your cameras. Okay, now I cannot see you for some reason. Okay, please, again, is there anybody, did anybody answer this part of the question? Mr. Carrillo, did you answer this question?
No, doctor.
No? How did you do the homework? In the homework, you had to do this part. You have to put your results in an external file.
Homework 2.
No, homework 1.
Homework 1, external force, and I can find the program.
Yeah. In the homework
Yeah.
1, you had to do this, right? You have to open a file and then write in this file. How did you do it? I'm really worried about that, because if you didn't do this, but you completed the homework, what can you conclude?
I
homework
don't
one?
remember, doctor, sorry.
No, no, come on. Mr. Nevares, you were going to say something?
Yeah, I don't remember to have that, to need that code in the homework 1. So I didn't do it correctly during the test.
Okay, Jimenez, were you going to say something?
Yes, doctor. Just write 3 lines to code to open the file, save, write on the file, and close. I remember that.
More or less, that's the idea. Good. Okay, in the second one was align it. Bars. This part of the question, it was just a way to check for me, a way to check if you did the homework. I'm really worried, because this is something that you had to do in the homework. If you didn't, please come and put yourself in my shoes. And what I have to think is that you're copying the homework. Okay? Try to be in my shoes. Okay? Put yourself in my shoes. That's exactly what you had to do in the homework. If you didn't do it, that means that you're copying the homework. And that's something that we don't like. Anyway, More or less, this was something like this, right? And you have something here pointing to the left, right? I think do you remember the properties on the left was? Does anybody remember the property on the left?
Yes, it was 2EA.
2EA. And here it was EA, right? Okay. Mr. Zamora, how many elements did you use to solve this? How many elements? 2 elements, yes. So we have 1 joint, 2 joints, 3 joints. Okay. How many degrees of freedom do we have in this case, Mr. Zamora?
Just 1, I think.
Now, in general, you have 3, okay? But what I think you're saying is that something like this. So this is D1X, D2X, D3X. See, we have to solve this because all the lines, all the bars are aligned. And then on the right-hand side, we have F1X minus F, because it points to the left, and F3X. And here, this is 0, this is 0. So basically, you're saying is that, Mr. Zamora, is that you're having only 1 displacement to solve for. So this is your K22. Okay? And then, if this point supports a force to the left, what happens with this part here? And what happens with this part here? If this section, because of this force, moves to the left, okay, this is what we're going to obtain for D2X. So D2X has to be a negative value, definitely. If this moves to the left, the midship section, the central section moves to the left, this part here, it's going to be in tension or compression, Mr. Iñiguez, this part here, this part of the bar, is going to be in tension or in compression?
In compression.
Yes, in compression. And this part here has to be in tension. So if you calculate P for this one, this value has to be negative. If you calculate P, that's the internal force for this part of this is this element 2, this has to be positive. Is there any way you can check this result, people? Is there any way you can check this result? If I give you P for the first and for the second element, is there any way you can check these values to be correct or not? Anybody?
If I add them up, they have to have the value of F.
Yes. So if I add P of 1, P of 2, absolute values, they have to be F. Yeah. Okay, in this case, the force here will point to the right, and similarly for this one. So these 2 should be positive, the reactions. But in this case, these are internal forces, people. We have to be careful. Okay, this here, these are external forces. And these here are internal forces. Yes, and that's the way we can check. See, we can see that this has to be negative, this has to be positive. If you take absolute values, they have to correspond to the absolute value of the external force, yes. So you can see that the system is correctly calculated. Questions about this, people? Miss Cumbe, did you get this problem? Problem 2, Miss Cumbe? Miss Cumbe, did you get this? Did you solve this problem, Miss Cumbe? No? Miss Vega, are you there, Miss Vega? Miss
Yes,
Vega?
doctor.
Okay,
Yes.
did you solve this problem too, Miss Vega?
I trying to solve, but I have a problem with the matrix. I evaluate with the angle 0.
Oh man. See, one of the problems that I see is that you don't read. I mean, I'm sure more than one people try to fool all of these values and all of that. And the problem is that you waste time. If you recognize that this is what you need, you don't need to write all of this. So all what you need to do is add the 2 values that go here and go on with the solution. Okay? So, but that's something that you need to do. You need to think. Okay. Next problem, it was a bars in the plane. Okay, it was something like this. There, and you have a cable. Okay, so this is cable. This is a tube. Okay, now we need to start by a global reference system. See, this is something that we have done. This is our global reference system. Of course, we have 3 joints. Let's call it this joint 1, this joint 2, and joint 3. Okay, so let's call this element 1, and this is element 2. Okay, so let's put here our table of connectivity. Let's suppose that I go from 1 to 2 for element 1. And for element 2, I go from joint 2 to joint 3. Okay, let me ask you something. Miss Lopez, what would be your theta for the first element? What's going to be theta for the first element?
0.
0 is, do you agree with that, Mr. Zambrano? Mr. Zambrano, do you agree with that? You see that minus what? See, if I go from here,
180, doctor, I'm sorry.
Yes. So that's your X and your Y is pointing downwards. So this is your theta, and that's going to be 180, yes. And for theta 2, if I go from here to there, let's use a different color, let's use green. So that's going to be this is going to be local X, is going to be local Y. Of course, I'm not going to write it there. I don't know, maybe about 50 or something, right? Okay, now, how many degrees of freedom do we have in this case? Mr. Zambrano, how many degrees of freedom do we have in this case? Our big K matrix, how big is going to be? The big K. Mr. Zambrano, are you there? No? Let's go on. No, somebody not here. Let's go down. Mr. Ruiz, Mr. Ruiz, how many degrees of freedom do we have for this problem? Okay, I'm asking you how many rows and how many columns this matrix is going to have. The big K, how many? No, please, let me ask somebody because I need to. No problem. But Mr. Ruiz, do you know how many rows and columns this matrix is going to have? Mr. Ruiz?
6.
Yes, it's going to be 6 by 6, yes. 6 by 6. Okay, now, the problem is stated that this point here moves, once you apply the force, whatever force this is, it says that this point moves downwards. So in this case, d2y is something that we know. Let's call it big 2y. So this is something that we know. Okay, the vertical component moves downward like that. Okay, of course, this and that don't move. So we have something like this. This is 0, this is 0. Then d2x, how much is d2x, people? How much is d2x? We don't know. We have to calculate it. Then we have d to y, and I put it capital D because we know it. So we recognize that we know that value. Then join 3 here also doesn't move. And here we have F1x, F1y. These are the reactions or the components of the reactions. How much is F2x? F2x, Mr. Alarcón. How much is F2x? How much is F2x, Mr. Alarcón? F2x. How much is F2x?
It's 0.
Yes. You shouldn't doubt. So F2x, oh, let me put it 0 directly. So we save some space. 0, so that's the value that we know. Okay, this is going to be minus F. And then on this upper joint, we need to calculate their reactions. It's going to be F3x, F3y. Okay, so in the first subsystem, how many equations are we going to solve for? In the first subsystem, how many equations do we need to solve for? Mr. Alarcón, how many equations do we have to solve for in the first subsystem of equations? How many? No? Mr. Nevares? How many equations in the first subsystem?
Only 2. Only 1.
Exactly. We see here that this is known, this is known, this is known, this is known, this is known. So that's the only unknown. So if I go in the next step is to solve this problem, and to solve it, we go in the first subsystem. And in this case, we try to solve for the unknown displacements. But there is only one. So we're going to solve for K33 times D2X, and is equal to, I'm sorry. There is an error here. Damn it. correct. Damn it. So this is d2x, and then we have to add k34 times d to y, and this number, we know it, and on the right-hand side, this is equal to 0. That's the only equation that we need to solve for. Okay, so this is known. K33 and K34 you need to calculate, and this is the unknown. So at the end, if this is the system that you need to solve, okay, there, I'm going to write it with this color. So we know that this value will come downwards, and this is d2y. This is data. Yes, you move downwards. And then from here, I can calculate d2x, okay? So d2x, you see, what's going to be the sign? What's going to be the sign of d2x, people? Tell me, anybody, the sign of d2x. Positive or negative?
Minus, negative.
So you think this moves to the left?
Positive.
Yeah, I think moves to the right. It's going to be very small, probably. But probably, let's suppose it moves to the right. So this is going to be d2x that you calculate using this equation. And what was the so in general, I would expect this to be positive. Okay, let's assume that this is positive. Okay, now the question asks you to calculate the force, internal force, which is developed by the tube. How do you calculate that, Mr. Jimenez? How do you calculate the internal force?
First we get the reaction.
But what for? You need the reaction.
It's in the point 1.
Yeah, you can do it, but in that case, you will need to calculate this and calculate that. Anybody else? Does any other idea? How to calculate P here?
We need to go on over to the local reference.
Exactly. Now, if this moves to the right, what's going to be the local x-axis for this? Don't multiply. Let me go back. Okay, this is your local reference system. Theta is 180. Yes, I know. But if this is your local reference system, how much is going to be the displacement of the second joint without any t? Let me repeat here. Okay, for this element, this is the local reference system and points downward. Okay, remember, let me go back. This element 1 goes from 1 to 2, okay? So this is the second joint of this element. Okay, so let me write it here. The second, second joint of first element. Okay, so we're saying that this moves to the right. So, but in our local, d2x is going to be positive or negative? That's a good question for you.
Negative.
Who said that, please? Your name? That's correct. It's correct.
Ruiz, doctor.
Yes, it's Mr. Ruiz. You're right. You're right. So you see that you're moving. See, this is the positive x direction, and you see that this point moves to the right. So this is negative. So to calculate P of the first element is going to be equal to what? Remember, this is D2x minus D1x divided by the length and multiplied by A. Remember, this is epsilon x, this is E. So this product gives you sigma and multiplied by A, that's going to be force. So how much is D1x for this element? D1x for this element. How much is this?
0.
Yes, yeah, this is 0. What's going to be the sign of P of 1? How much is going, what is going to be the sign of this P, of this P force? It's going to be negative. Yes, somebody said that. It's going to be negative. Because this number is negative. E and L are always positive. So the result is going to be, makes sense that this is in compression? I think so. If you pull downwards, this is going to be in compression and the cable is going to be, needs to be in end tension. Somebody was telling me that it was very long. Mr. was the last name with A, Mr. Alarcon. Do you think this is very long? Mr. Alarcon?
Yes, doctor. That is the for the matrix.
Do you still think that this is long?
When I resolve different, but I have.
I know. There is always some tension. Yes, I understand. But this is something that we need to handle. Okay, before we start shooting, we have to aim. You have to think. Otherwise, see, I didn't ask to write all this matrix because it takes a lot of time. A lot of time. Okay, if you start writing 36 values here, so that's a lot of time. But you have to, that's the first element. That's the second element. You start calculating each one of these values. That takes you probably half an hour. But that's a waste of time because you don't need all of this. But you need to recognize that after you do the homework. That's my concern. Okay. And the last question, let me go to the last question. Okay. It's a review on beam bending. Okay, so this is a typical analysis, and we have analyzed this in sheave structure, I'm sure. So you apply two forces here and here, and this is symmetric. Okay, so in this case, if you apply a force here and another one here, this is symmetric, the reaction has to be here equal to F. The reaction is going to be here equal to F. So if I write shear force in this part here, Mr. Barba, in this area here, if I make a cut here, the shear force here is going to be positive or negative, Mr. Barba? Shear force.
It's negative.
Negative, yes, because this is a positive phase, and since the force points upward, here you need a negative, a force pointing downwards, which in our convention is negative. So this is minus F. So in this here, in this region, if I make a cut here, I have 1 and 2F's, they cancel. So here you don't need shear force. And in this part, you go again to that. So in this area, you have no shear force. If I plot the bending moment, this is the shear force is constant. Remember, the shear force is the opposite of the slope of the bending moment. See, the mz dx is equal to what? Minus v. So in this area, in this part of the beam, you have a constant negative shear force. So this is equal to plus F. So that means that this bending moment is aligned with a positive slope, and it starts in 0 because this is simply supported. So we go like this. In this area, the slope, the shear force is 0. So that means that this is constant. And here is the opposite. So we go back to 0. Okay, if this is F, how much is this bending moment? Mr. Iñiguez, how much is this bending moment? We need the distance here. I'm sorry. This is data. This was data from here to here. I think we put it a distance here. And we have a total length of whatever. So how much is this distance, Mr. Iñiguez? How much is this distance, Mr. Iñiguez?
Sorry, doctor, I don't got it. This.
See, I have L, that's the total length of the beam. A is the distance between the two forces. So if I subtract L minus A, I have the combination of this plus that. So since this is symmetric, this has to be equal to the difference, but only half of that. So let's go back to our bending moment. How much is going to be the bending moment? Miss Cumbe, let me go back. No, Miss Vera, it's turn. Miss Vera, how much is going to be this bending moment in this central region of the beam? How much is going to be this, the bending moment?
F by L minus A over 2.
Yes, yes. So that's the bending moment. Now, sigma is equal to what?
Bending moment minus bending moment, distance over inertia.
Yes. And this is equal to what? This is equal to E times epsilon x. This is something that we know. Okay, this is what we measure using a strain gauge. So we know this value. It's a very small, say 10 to the minus 6, but in general, in our lab, since we measured micro strain, the value was very large for our standards. And from here, this is what we need to calculate this. We can define inertia divided by Y max. And from here, this is something that we know. So we can calculate E. Okay, this is very simple from a, you can see in the literature, this is a test that people do in order to get the E value when you don't have an universal testing machine. This is because it's very simple, very easy. And in this part here, in the central part here, you have no influence of shear. Okay, so here you have only normal stresses in the central part. Okay, that's why we say that there is only sigma x. We don't have to worry about any other type of stresses in this area. Okay, let's take a break here. And when we return, we can go on with the rest of the material. Okay, let's take a 5-minute break before we can go on.